Okay, great. I'm happy to introduce the second speaker of the day. We talked about telecom networks, coincidentally, in the last bit of the first talk. So here just going to be, I think, more of them. So the speaker is Maryam Daryalal. Maryam is Assistant Professor of Operations Research in the Department of Decision Sciences at HEC Montréal Business School, where she focuses on developing new methods for decision-making under uncertainty with applications in various areas like telecoms, healthcare, supply chain, and so on. A lot of her focus has been on telecommunication networks. She's been active in student organizations. So she's received the Judith Liebman Award, Connaught International Scholarship, and those during her time as a graduate student in operations research here at the University of Toronto in mechanical and industrial engineering. So we're happy to see her speak from the other side today. So Maryam, please go ahead.
Thank you, Elias. Thanks you and Alex for inviting me, and thanks everyone for joining us today. I will talk about a problem in telecommunication, which arises very frequently. It's the network migration problem. We'll see what that is. And we attack this with a hybrid logic-based vendor decomposition framework. This is a joint work with Hamed Puya and Marc-Antoine Dos Santos from Siena, the telecommunication company. All right, so I will briefly go through the problem definition, then we will see the solution methodology and some results. So what is this network migration problem? Imagine a telecommunication network. Naturally, we can model it with a network, with a graph. And in this telecommunication network, we have a set of sites that would be our demand points. So it could be like Montreal, Toronto, these different sites that request a certain number of connection requests. And there are circuits between these demand points. Note that this demand points is not like between our computers individually. These are rather larger aggregated set of demands. So the circuits get a request from this particular set of sites, and then it transmits the request to the other point. But the thing is, as we know, telecommunication networks, they face a lot of technological advancements. So as you're buying more and more this fantastic services from telecommunication companies, they are in the background updating their technology. And this is very often. But the issue is that this whole thing is quite complicated. This process of upgrading is quite complicated and expensive. So imagine a whole continent like North America, that there's a telecommunication company that owns a lot of the backbone network in that continent or country. And then the way that the upgrade works is two synchronized technicians. They go to two end points of the same circuit, where this could be stretched across the continent. Like it could be, one of them could be in California, the other one could be way up in Quebec. And they have to, in a synchronized fashion, unplug both endpoints of the circuit and plug them in the new deployed network. So here we assume that the new deployed network, the infrastructure is already there. We have like the telecommunication company has already deployed that network. It's just now we need to upgrade and migrate from this network that we're already working in to the new one. And the way it works is they both at the same time disconnect one circuit from the old network and move to the new one. And why is it in a synchronized fashion? Because, well, we don't want to get disrupted too often. And telecommunication companies, usually the main customers that they are dealing with is not just individuals like us. It's actually like it could be a hospital. We can't let a hospital get disconnected off the network, or this the police station. So when they buy these type of companies, when they buy a service from telecommunication company, they sign something, a service level agreement, to make sure that they don't experience too much disconnection. So in order to minimize that, this whole process is done in a synchronized fashion so that the customer experiences the minimum amount of disruption. And it's usually done within a maintenance window within the night, so that, yeah, the probability of people experiencing disruption is minimized. So, and naturally, what we are looking for is the upgrade order of the circuits, because the job, I explained it in a very simple way, but actually the technician is a professional, and it's not just unplugging a USB thing. These technicians, they are rare. So sometimes we actually need one technician to move around and across a continent, and we need the upgrade order so that the synchronized technicians across a country or a continent or a city are able to migrate the old network to the new network with minimum cost. So we have a lot of constraints, as I mentioned, like the number of circuits that can be migrated within a particular maintenance window because of the amount of disruptions. We need some engineers as well. We'll see that the engineer is the one that gives the go to these two synchronized technicians. So that engineer, again, is in high demand. So that one is limited as well. So we have various operational costs that we have to be careful about. So this is an example. This is my beloved Canada. And let's say this is just completely imaginary. Let's say we have divided this country into 5 regions. And in each region, for example, here in the Vancouver side, there's just one technician. Up north, there's 2 technicians. On the east side, we have 3 technicians. And this is the backbone network. So this is the network that carries the majority of the amount of requests. And every one of these points, every one of them is a site that hosts a couple of circuit endpoints. And we assume, because of the operational restrictions or the time that it takes for travel, the technicians, they can travel between sites, but not regions. And these are our remote engineers that give the go to synchronized technicians to start the process of migrating. And the solution to this problem could be that, for example, this technician that was in region 4 becomes responsible for all the circuits in site 9. These 2 technicians, they go to site 8 and site 7 to do the migration. This technician here makes a travel between this point and this point. So this is a sort of a solution that we are looking for. So this is a possible assignment, not the optimum one, but just a possible one. And for example, this technician now is not assigned to anyone. All right, so we define this notion of a plan for every NMP instance, network migration problem instance, that relies on the notion of a shift. So what is a shift? That's exactly what you can think of. A shift for a technician would be the number of the circuits that a technician migrates between every site pair, and also the path that the technician should take among the sites. So sort of the job that it needs to do. And then a plan for us is just a set of shifts. So we're looking for a feasible plan, a feasible set of shifts that would migrate all of these circuits. And well, it's feasible regarding the service level agreements, regarding the number of circuits that can be migrated in a given maintenance window, regarding the time travel and everything. So if we want to have a sort of idea of how a feasible plan looks like, for example, this could be the plan for that example that we saw in region 1. I had 3 technicians, and for each technician, I am saying, for example, between in site 1 for the site pair 1 and 3, this technician is responsible for migrating 1 circuit in the same site. For the site pair 1.5, this technician is responsible for migrating 3 circuits, and so on and so forth. And here in region 3, we not only have 1 site, but also we have travel. So this travel, this is a very simplistic case, but this travel requires routing. All right, so this is the final framework that we're going to see how it is built. Because of the recommendation of the reviewers of our paper, I brought it to the beginning because they mentioned this is one of the most complicated decompositions. So I'm bringing it here, and then I'll get detailed in each one of them. So we are going to solve this problem with a logic-based Bender's decomposition method. And in this logic-based Bender's decomposition method, we have different levels of decomposition. So for solving the problem, we have a master problem that would be the LBBD master. We have a sub-problem that is responsible for something else. And then for solving the master problem of this LBBD framework, we have another levels of decomposition. So I'm just going to go and start with the higher level. So the main loop is when we solve the master problem, and then we pass on some solutions that we'll see what are they, this hat solutions. We pass them on to the sub-problem, the CP, which is going to be a CP model. And in a logic-based Bender's decomposition fashion, we're going to try and solve the problem. So in the main loop, in the main decomposition framework, what we're going to do is, in the first step, which would be the master problem, we're going to find an ordering of migrating the circuits, but not a complete feasible ordering. So we're going to make sure that the ordering that we're finding in the master problem in the first step is something okay-ish that satisfies some of the constraints. So this ordering is going to migrate all the circuits between every 2 sites. So I'm just going to say, for example, all the circuits between site 1 and 3 should be migrated, but how? The first 2 are going to be migrated first. The next 3 is going to be migrated the second. So I'm just going to find an ordering of all these circuits. And then, I'm sorry about the noise, and then we're going to make sure that at every maintenance window that we found this ordering, at every maintenance window, exactly the same number of circuits are being migrated between site pair SS prime and site pair S prime S. So we are not our solution is not something completely wrong. That is migrating 1, 3 between site pair 1, 3, 2 circuits, and between site 3, 1, 5 circuits. So that can happen. We said these circuits, they have to be migrated, the endpoints, they have to be migrated right at the same time in a synchronized fashion. So at least we make sure that the number of circuits that are migrated between every site pair is equal. So that's the first step. That would be the master problem. And then in the second step, we'll look at that solution and we'll make sure that it's a feasible ordering. What means a feasible ordering? It means that we have a feasible route. It doesn't have loops. The technician can't jump from this side to another side. There should be a feasible route. The time restrictions are respected, considering the time that it takes for travel, the time that it takes for the migration of these circuits. So we do that. And how do we do that? We find a feasible plan for this ordering. So I give the ordering to my subproblem, and my subproblem tries to see whether this ordering that I gave is feasible. So it means that it can find a feasible plan for it regarding those shifts that we define, and it's a valid one. So step one would be where we solve our LBD master problem, which is a MIP. And we define this notion of MSS prime W. That would be the number of circuits that is being migrated between the site pair SS prime at a given maintenance window. And then this is the solution that is passed to the subproblem. So subproblem gets this number of circuits that are migrated at every maintenance window between every two site pair, and then it sees whether this is doable. And for checking that, we are using a constraint programming model, and that's our subproblem. So that constraint programming model, the subproblem, it looks like this. So it relies on this decision variable XRTS, which is a time interval decision variable in the context of CP. So this one gives us the time interval where this this technician T is working at site S, and this R is the region, but that's just a technical thing. So this time interval variable would give us everything that we need for our plan. So it would tell us that this particular technician is gonna work at this particular site. For every maintenance window, we're gonna see whether it's doable with the given decisions, with the given values for MSS prime W. We're gonna see whether it is possible to move those circuits that master problem has told us to migrate in maintenance window W between sites SS prime. So we're gonna see whether it is possible, and if it's possible, we're gonna find the best plan for doing that, and that would mean finding the minimum cost of such a plan. So at every maintenance window, what I'm gonna do is I said I'm going to move and migrate circuits between site pair SS prime, and I have this for every site pair. It's given to me from the master problem. So at every maintenance window, I look and I properly distribute this SS prime circuits among the technicians that are available. And what does that mean? Well, it has a couple of conditions. For example, the same technician can't be at both sites at the same time, like a couple of logical restrictions, which are taken care of with some constraint programming restrictions. And then after this distribution, I look and using this very beautiful constraint no overlap in constraint programming, I find the sequence of these time intervals, where these time intervals all put one after another, that would give me the route that I'm looking for, the travel route of every one of those technicians. So with these two, I make sure that the distribution of these circuits among the technicians is correct, and also there's a valid route between the sites when different circuit endpoints are assigned to a technician in different sites. But that's not all. We have to make sure that the time that it takes for doing that, it is a valid time, and also we want to find the minimum cost. So we find the working time of a technician if that technician becomes responsible for migrating those distribution of circuits that we assign to it, and also the travel time that it takes. So we find the working time, we make sure that it's it's not the person is not going to work overtime. And also the number of engineers that we said we need remote engineers to give the go. We make sure that that is respected as well. So using this constraint programming model, I check whether the distribution of the the circuits among these technicians is correct, and whether it is feasible to actually do that ordering that the master problem suggests. All right, but how to decide on the number of the circuits? So those M parameters, in fact, decision variables in the master problem. How should we design a method so that we, in a smart way, pass on solutions to the subproblem? So we don't want to do that in an exhaustive way because it takes, believe me, it takes forever. So we're gonna see how it's done. All right. So master problem is going to pass on this M solutions to the subproblem. The subproblem looks whether this is feasible. If it's not feasible, it adds some LBBD feasibility cuts. I'm not gonna get into detail about that. And if it's feasible, then we're gonna check whether it's optimal. If not, it's gonna add some LBD optimality cut and go back to the master problem. Otherwise, we're done. So for the master problem, though, we don't want to do an exhaustive search. We want to pass on some information to the master problem. And for passing on this informations, we are going to, so I have 5 minutes. For passing on this information, we're gonna rely on a relaxation of the master problem. And it's a sort of standard way in LBBD terminology. And for that relaxation, we're going to keep the first stage decision variables as integer, but we're going to relax the second stage decision variables. So, and that would lead to a sort of Bender's decomposition. So here, first stage and second stage, it's by the way that we have defined them. It's not in the sort of actually two-stage stochastic programming. So we have defined a set of decision variables as the first stage, a subset of them, and the ones that are decided after deciding on the first stage decision variables, we're considering them as second stage variables, and then we add the apply Bender's decomposition on that. So now we'll have a master problem for the Benders and the subproblem for the Benders. We pass on solutions to the subproblem, and then the usual stuff for the Bender's decomposition, Bender's feasible, Bender's optimal. And if everything is good, then we pass that set of solution to the CP model. But again, this subproblem of Bender's here is super difficult because you can think that this subproblem is sort of representative of this CP model here. So finding out whether this is a valid ordering, it's just we made it continuous. So the way that we're gonna handle that is sort of using an extended formulation where we attack it with column generation. So I consider this set of all possible shifts. And then for every one of them, I define a decision variable that says how many times I've used this shift. In the LBBD subproblem, which was the CP model, we were trying to find a feasible plan for the migration. So naturally, those shifts, if we look at it in this context, those shifts were integer. Now, in the Bender's one, we said we're gonna relax the second stage, which corresponds to the shift. So now I'm going to let them to be fractional. And then we're going to solve a column using a column generation method. We're implicitly enumerating this set of all shifts. And in solving the Bender's subproblem, well, it's a sort of standard way of solving it, solving this, defining the pricing problem. So this is the MIP model but we also add another CP component so that we can accelerate it. And we show that using both CP and MIP as the pricing problem, it improves our performance substantially. Okay, so I'm gonna just go over these. Yeah, in the so now for solving the subproblem, I have the master problem of the column generation method, the subproblem, which involves both MIP and the CP. I check whether it's optimal or not. If not, I add a column. And if yes, I go to the subproblem for the vendor's problem. I go to check whether the solution is feasible. All right, so just a couple of numerical results. These are real networks across different countries. This is across the city, this is across US, and this one is between countries in Europe. And what we did was we applied our method, and we were able to solve these instances with acceptable gap. So this is the first exact method for solving these type of problems. Therefore, there is no alternative. And here you see the computational effort that is divided between every one of these solution paradigms, and the gaps that we obtained, it was good. So the solution quality was quite acceptable. For the column generation, we also showed that adding the CP, adding the CP and MIP, it substantially improved our performance, as you can see here. So when we only had one type of subproblem, the gaps could be as large as 50%, but then when we use this hybrid way of using the pricing problems, the gaps, they reduced quite a lot. And that's all. If you like to have a look at the paper, it's here. It is published in IJOC, Informs Journal of Computing. I will also present it at Informs annual meeting for the best paper prize in telecommunication. So we're finalists, finger crossed. We'll see how it goes. Thank you.
Great, thank you very much. Congratulations on the nominations. So we wish you the best of luck.
Thank you. Thank you so much.
Okay. Alex, should we first stop the recording? I'll let you do it. I don't want to ruin the saving to the cloud.
Yeah, sure. Just maybe for the YouTubers out there, we also have a next DOTS, and for everyone attending, we have our next DOTS in a month. So we're doing 2 more DOTS this season. So next Friday, the next Friday, November. I can't remember, is it November 6th at this point? We will have our next DOTS. So don't quote me on the date, but it is sometime in the first Friday of November.
It's on the website.
Yeah, it's on the website. For the mailing list, I encourage you all to check your spams. I mean, I guess if you're currently in the room, you probably received the link, but if you might want to add the mail address lists at mixedenergy.org to your approved, to your address book. Otherwise, ours tends to go to spam for some reason right now as we switch to a new mailing list. But yeah, whether you're attending in person or watching this recording later, thank you so much for supporting DOTS. I hope to keep seeing you here, and we'll now go to the breakout rooms.